Last time we had introduced the concept of a derivative. F prime of a represented the derivative of the function at the point A. We talked about the derivative as representing the slope of a tangent line of the function at the point A. Now, the other version of the derivative was in terms of a shrinking interval. So a time interval whose size was h, and then we make h get smaller and smaller and smaller. So another way of thinking of the derivative is the instantaneous rate of change of the function with respect to the variable x at x equals a. Some examples that we're going to use. If I give you the function f of x, x squared, I would like to find an expression for f prime of a. So according to the first version of the definition, we would plug in x squared minus a squared, x minus a. I've been trying to convince you that every time you have a strange limit, you should sneak a peek. Here you'll see 0 over 0, so no limit laws, but you can do some algebra. And in this case, the algebra is very simple. You could factor the top into x plus a, x minus a, and that's what's going to locate the 0 over 0. And so you'll be left with a limit that's really straightforward. It's going to be the limit of the x plus the limit of the constant, and that's going to leave you with a 2a. So in this case, the derivative gives a nice little expression. Another option here would be to say, okay, if the function f of x is absolute value of x, let's find the particular value f prime of 0. So I'll do this using the second form. F of 0 plus h minus f of 0 over h. You'd get an absolute value of h minus absolute value of 0 over h. And so this would end up giving you a limit as h approaches 0, absolute value of h over h. And this is now a 0 over 0 limit, so no limit laws, but you have to do some algebra. The algebra here is that the limit is going to have to be considered in a two-sided manner. So if we approach from the left, this would end up giving me a negative h over h, which would be a negative 1, so this limit would be negative 1. Now on the other side, if we were to approach, we would have a positive h over h, which would be a limit of a 1, and the limit would be 1. So here we would say that f prime of 0 does not exist. How should we interpret this? And so where we will go forward from today, the new idea is that the derivative represents the value of a slope or a rate of change at a given point, but we could also think of the derivative as a function. So the answer that we got earlier was f prime of a was 2a when the function was x squared. Now, function notation is powerful, and it says, you know what? We could really just use any letter we'd like there. So we could think of that derivative answer that we got as just a function of x. We need to be able to interpret the derivative as a function. And to try to show you that, I'm going to go through yet another example. But this time I'm going to use the definition that's essentially like the old one, but instead of using the letter a, we'll just use the letter x. So this will be our definition of a derivative. And rather than plugging in an a, everything essentially feels the same here. So we'll have the limit as h approaches 0 of the square root of x plus h, because that's what this first term means, subtract the square root of x, because that's what this second term means. Now, as always, we sneak a peek. Whenever we deal with derivatives, we're going to see a 0 over 0. There's going to be no limit laws, so we're going to have to do some algebra. The nice thing about this algebra is that we have practiced it many times in the context of limit laws. And in particular, the right algebra to do here is to multiply by the conjugate of the numerator. And when we sit there and expand everything out, we'll end up with an x plus h. The terms with the roots will cancel each other out. I'm just going to be lazy and write them like this, and I'll have an x at the end, and then all this stuff downstairs will end up looking the way it does here. Now, the other nice thing that happens is that these x's will cancel out, and you have to do a little bit of algebra to eventually find that 0 over 0. When you do, it becomes a very straightforward result to work with. And so generally, when you've got a limit and limit laws, you try to do some algebra and you work as far as you can and see what you end up with. Now, in this case, we are going to get some expression that is not 0 over 0, so we could use the limit laws. And so when I use the limit laws, I'll get the limit being distributed everywhere here. Now remember, the limit variable is an h, so we have to pay a little bit of attention toward that. And what I mean by that is in the second instance, the square root of x, you don't need to pull the limit in and out because the limit variable is an h. We see a 1 over an square root of x plus 0 plus another square root of x. So the final result is 1 divided by 2 root of x. It's a function of x. We started off with the square root function, and its derivative is 1 over 2 root x. Now, what am I supposed to do with all of this? How to interpret this? Typically, we're all aware of how the square root function looks. What does the derivative function tell me? So this derivative function tells me the slope of the tangent to the function at the point x. So if you pick a value for x, I can tell you the slope of the tangent. So for instance, if I say f prime of 1, I would take in the value there and I'd get a 1/2. Now if I were to go to the graph and draw in a tangent line, its slope would be a 1/2. If I were to say f prime of 4, and if I were to go to the graph of the function, draw a tangent line, I would see that its slope there would be 1/4. This formula will calculate the slope at any value. So you pick a value of x, and if I can plug in the number and get a result, that will represent the slope of the tangent line. Now note, if the derivative exists at a point x, we say that the function, the original one, not the derivative, is differentiable at x. Differentiable means it has a derivative. The function I was working with here, square root x, it has its own domain. From 0 to infinity, 0 with the square bracket. You are completely allowed to take square root of 0. But the domain of the derivative is different. It's nearly the same, except you are not allowed to use the value of 0. So we say that because of this domain, that the original function, square root of x, is differentiable on the interval 0 to infinity with round brackets. And so you might say, well, why? What is going on? So what is preventing the derivative f prime from existing at x equals 0? If I were to take a look at that square root again, I look at the graph and I say, well, I don't get it. What's happening here that is causing some issues? So in the next video, we are going to answer that question.